everyone. Thanks SSU once again for giving me this opportunity to talk about C++. I don't nowadays do as much C++ as I used to do. I work at LinkedIn now, so as you might guess, it's all Java. I got sucked into the dark side of managed code. But I still work for Microsoft because LinkedIn is technically Microsoft. They still continue giving me MVP award for 1 year, I guess. I don't know what's going to happen next year, but that's good. So when I was thinking of this talk, I was wondering what title I should really give, because I presented pretty much the same material in the Silicon Valley Code Camp back in 2015. You can see 2015 there, on the wall somewhere there. And back then I called this talk Composable Generators and Property-Based Testing. A little bit scary name, and maybe that probably drove people away. And so I'm kind of redoing this very similar talk today with much more audience. Back then there were about 6 people, one of them left, and said, okay, this is not me. So the idea here, well, another way to perhaps to call the same content is functional API design in C++. So you could look at this in many ways. So I was not sure which title I would give, so I just put all of them here anyway. So how many of you are familiar with, say, Haskell or Scala to the level that monoids, monads are your second language, or second nature? Can I get a show of hands? Just trying to. All right, we have one person. Well, you're not going to learn anything in this talk. Absolutely. So for others, this is an attempt to kind of demystify that terminology. I was in the same boat like yours back 2014-2015 time frame, and I was going to the same, what are these fancy words? What do they really mean? And can I express them in the language I know and I use for work? And that's how I went down this route and ended up creating a library we'll talk about in a second. So that's just that. So that's where I'm coming from for this talk. And coincidentally, this year I also reviewed a book called Functional Programming C++. This is by Ivan. I don't know how I'm probably butchering his last name. Suki or Kyuki, something like that. By Manning Publication. It will be out pretty soon. And this talks about a lot of things. Like it definitely helps you. If you have no idea of functional programming at all, then it brings you up to the speed. You can be a beginner to intermediate functional programmer in C++. Right, to the extent C++ offers this. And yeah, it's a pretty interesting book. So last time, I think it was September, end of September, the week of CPPCon. I had another presentation. I took some examples from this book and went over some things that I learned while reviewing it. It was pretty interesting exercise for me as well. I'll touch upon one thing from that presentation as well. I wish this book actually had the material that I'm going to talk about today. In fact, I suggested the reviewers, the publisher, or the editor, I think, to consider having something like this, like functional API design, and maybe an example of generators. Like you can look at this, my earlier talk, and you do you think there is space for this? Because I think without a book like this cannot be complete. I think that's my opinion. So I guess there is an opportunity to write another book with perhaps some material like this, which we discussed today. All right. So I need to give credit where it's due. This work was done when I was working, at RTI. So it was about 2 years ago, and RTI develops connectivity software, connectivity middleware for industrial Internet of Things called ADS. So that's when I did this work. Okay, so why should you even care about functional programming? You know, it tends to be pretty different and kind of makes your brain work in a different way. Like, why should you even learn something and try to mend your ways? If you're like me, like you write software for a living, then you probably want to write bug-free code. That's the first order of business. Write it nicely, expressive code, and then maybe you want to look at functional programming because it gives you those opportunities to write that. And then you want to be productive. You want to write maintainable code, extensible, modular, and all that. All the good things that we strive for. So functional programming gives you those aspects, those features in your code, provided you go follow that style. And of course, it also can have a lot of fun while doing that as well, because the code feels very different when you look at that, in a functional style of design. Okay, so we'll talk about property-based testing today, very briefly. Nothing very serious. And then why we really need composable generators to do property-based testing. And I'll share some implementation of a functional generator library written in C++14. It's actually really small, less than 1,500 lines of code, including comments. Not that it's heavily commented, but yeah, pretty small library. If we have time towards it, we can even talk about how a coroutine can be wrapped in this library, so that coroutine acts as a generator and you can just plug it in wherever you are using this. Then we'll talk about the mathematics part a little bit. I don't claim to be an expert in these functor, monoid things, but I think I have understood them enough that I would really like to share that and perhaps really test like whether I have really understood to a level that I can explain it. And we'll talk about type generators. That's going to be fun, generating random types at compile time. That's not necessarily functional, but it's metaprogramming. So in a way, yes, it is pure functional because it's C++. All right. So what's a property? So sometimes when you write software, that you can actually say that look, some invariants can be held no matter what. For example, reversing a linked list twice gives you the same list back, right? You can say that for any list, and reversing it twice is the same as before. It doesn't matter what type it contains, how many elements it contains, and so on. Compression usually makes things smaller, so that's the property of a compression algorithm. You want to test it. This better be true in all cases, well, almost all cases. And a serialization, deserialization library, you could say, look, if you serialize something out and deserialize it back in memory, you should get the same input as the earlier output. Well, you should get the same output as before. So we'll look at actually a deserialization library called RefleX. By the way, questions are fine during the talk. Yeah, go ahead.
What do you mean by no effect? So do you mean by no side effect?
Yeah.
Okay, so it's kind of, yeah. So that's how they use that side effect.
Even if there are side effects, this should hold true.
I understand that. So the terminology is a little bit different than you use that no effect or no side effect. So I just
right.
try to
no side effect in a sense, right.
Yeah, just point that out.
Sure. Okay.
So when you say no effect, what do I do that for? No effect.
A test, though, right?
Yeah.
So there may not be any visible effect of a function, an expression like this, but it's actually verifying that serializing and deserializing the same thing gives you the original.
So that's why they call side effect. No side effect. So
no side effect.
Yeah.
Yeah. There is no side effect of this expression.
Okay.
Other than, yeah.
So that's what you mean, right? Okay.
That's what I mean.
Okay.
So yeah, property based. Yeah.
Well, so I think you mean what the code says. Not I mean, I don't know that necessarily talking about side effects here is important. What's important is that if you reverse a linked list twice, then it's equal to what the
Original
original
list.
input is. So I wouldn't think about it in terms of effects, I would just think about it in terms of these expressions are true.
Yeah,
Right, assuming,
I understand that. But they are using side effect instead of effect. But that's just terminology.
Okay. All right. So we're talking about properties, right? So we generally don't write tests like this. We don't try to verify invariance in this fashion. We tend to write examples and boundary conditions and so on in testing. But this could be one form of test, right? For your serialized and deserialized algorithm should hold this property. So the RefleX library, which I was working on back in RTI. So it works on C++ classes and structs. It takes your code. It's all pure library, error only, and turns it into a schema and data. So think of it as Avro or protocol, Google protocol buffers. So similar to that, RTI has DDS X types. It's essentially a way to represent types at runtime and a way to serialize data for embedded systems and Internet of Things kind of systems. So RefleX library acts like a code generator written all in C++. So the original use case was like the customer had a custom code generator based on XML, and it used to read XML and has actually generated code with C++ types and everything. They wanted to use DDS, want to serialize data out as DDS X types would, that specific format. But they really don't want to change the code generator because that's how it was built and it was custom. So, well, one way to do that is take their C++ types directly, plug in this reflection library, which is not a runtime reflection, it's a compile time reflection because in C++ we can do that, and produce in a sense using templates, produce data and types just like regular code generator would. I don't know, I don't think I got that right. But essentially, you want to start with existing C++ code, use RefleX, hash include something, and out comes a schema at runtime. We'll see an example of that. Any questions on this? So let's consider a simple example, a shape type, and it's a very typical class. There is a string and x, y, and shape size. There's a constructor, few, getters and setters as just one function. So this type, of course, cannot serialize itself, right? There is no functionality in it. But let's say you cannot change this type in any way. So what you can write is something like this: RefleX adapt struct. And those who are familiar with Boost Fusion would probably immediately recognize that it's using Boost Fusion, and you would be right because that's what it's doing. Although it extends some of its the preprocessor macros with things like key over here. So it actually accepts 3 tuple instead of 2, and it generates more custom code because it's a key. So the way that's some annotation that DDS would use. Like, okay, color is a key, so it has some special treatment. Rest of it is just same. So x, y, and shape size return int. This unfolds into pretty horrible looking template code if you really look into it, but that's not going to be important. Yeah. So that's RefleX, right? So how would you test RefleX? It does its thing, but I want to make sure that even if you throw at it any type whatsoever, any generated type, like by a proper code generator, it should work. And it's not really the design, the space is pretty big, like you could have arbitrary types. So here is a property test in RefleX. So you create a type manager, which is essentially by this you are creating a schema for the type T. So type manager will hold a schema internally. And now you use create dynamic data, and in is the input of type T, any C++ struct type, and you create dynamic data, and it essentially now you have even the data part. You can think of this as a serialization, pretty much serialized type. It has not been serialized anywhere, it's all in memory. You could think of it as a single buffer that's held by the safe dynamic data. That's ready to be sent out on a network or in a file or whatever. The test reads it back out right away. So now you read dynamic data, the one that you just created, safe dynamic data, and puts it in out, and out is a temporary up there. So now you just serialize back out, in should be same as out, right? Because it's the same property test we saw earlier. This is the actual one. Well, there is a very important question though. What is T? And what is in? What is the data? The test makes sense, but what is the data? Because harder question is what is the type? You could create a few types manually and maybe create a lot of, say, corner cases, a bunch of structs, maybe tuples if you are into it. But I don't think it gives sufficient confidence, like, okay, is this really going to work? Because there are so many corner cases, because serialization library has to get the alignment right, and then, I don't know, a whole bunch of things like inheritance was also supported, a lot of things that you have to think of that, is kind of effort, a lot of effort. So coming up with really interesting T's and data is hard. And that's where the whole data and type generators came in. I think we briefly talked about this earlier. So property-based testing allows you to do complementary testing to your regular example-based testing. You specify some post conditions that must be held true. And I think it really helps you think harder about your code, because you really want to make sure that the invariants in your library or your implementation are correctly implemented. It's more declarative, but it is declarative only if you can have a machinery that generates data and types for you. So you just write this property test, and something around it, which is the generator machinery we'll look at, produces the types and data to hammer your test. And it's actually programmer's nightmares, because a machine is trying to hammer your test case in literally unthinkable ways. We'll see later on in the examples. And it really helped identify corner cases and some bugs in even lower level libraries because of this. So it ended up being paying off. All the effort was worth it, I think. So this is nothing new. Haskell's quick check and Scala has this already, perhaps other languages as well. Good property-based testing frameworks can they recognize, okay, for a certain input, your test fails. That could be an extremely large input. They can shrink that input down to the smallest possible one that causes your test to fail. That's kind of neat. I didn't do that. But essentially, free reproducers. It just runs the test, finds this thing, shrinks it, and that's your reproducer, go fix it. So, kind of neat in that sense. Alright, so that brings us to the main abstraction. Now the first main abstraction today, which is data generators. That's a little bit simpler than type generators. So we look at, that's the second main abstraction, we'll look at that towards the end. Alright, so now it's going to be sort of switching gears. Like, it's very different. So we know the reason why we're doing this. Now I will start at the absolute, the simplest, lowest level actually for data generators. So simplest data generator would be a random number generator. It doesn't make you think at all, right? It just whips up a random number out of nowhere. And well, you provide a seed if you want to. And that will be that in C. Just called random. So because this is a C++ meetup, I feel required to state something like this, which is kind of much more verbose than my needs. Chrono system call would give you a seed. You do that, and then you can instantiate a standard random number generator, one out of many, with that seed, and just call empty. That's a function object that you can call over and over to get random numbers. It's kind of neat. I mean, you can customize a lot of things here, distributions and all that. You cannot do that with random stuff there. But we don't need any of this in the bottom. Okay, so we have a simple random number generator. Now, sorry, question?
Okay, sorry, I can go back to the last slide. Sure. I have a bit of a bone to pick here. If you do this, and a lot of people do this, of seeding your random number generator with time, your tests are not going to be reproducible. You shouldn't be using a random seed, just pick some seed. I was doing 1 through 27. I don't know why, just a number of things.
That is right, and this is just an example. Later on, we'll see that the actual build uses it generates a random number from the shell, and if the test fails, it dumps a random number into a file saying that, look, I just use this, and something failed, bad happened here. You probably want to plug this in, and you want to reproduce the same thing. I think I should not actually go over there because that's kind of I don't know. I'm revealing too much before really going through. That's not the progression I want to go through. That's fine. But you are right. Reproducibility is important, and we won't lose it. So let's create a very simple generator, a bool generator, just mod2, just flips up random bools. A uppercase character generator would be you just add 0 to 26 in A, and that will be that. So we'll probably see where this is going. I'm going to create generators for primitive types, and then we'll take those into more complex structure types and all that. So that's a uppercase character generator. You can have lowercase and whatnot. Double is pretty similar. Floats are similar. Excuse me. Slightly more interesting generator would be a range generator. You provide a range between low to high, and it generates a number, a random number in that range. Note that we want to create random input, right? And not necessarily all random input doesn't really make sense. If something, if your type is shape type, right, color, or maybe person's name, maybe you don't want unprintable characters. That's just not supported. Or maybe if it's color, then there are only limited number of options, like red, green, blue, whatever. I don't know. California won't make sense as a color. So you don't want that to be generated. So we want control on that eventually. It's not going to be all random input. But we'll start with random numbers, which will require us to kind of control them in some systematic way into something we really want for our application. But still, it will be fairly random. Like we'll take a look. So this range generator is kind of inconvenient because you have to provide this range all the time. Instead, we can return a closure like this. It remembers low and high, and when you call this function R, in this case, it's not a function, it's a closure, it will always generate one out of these, because that's what the range remembers. So now you can pass this range generator anywhere you want to generate random numbers in that range. So we are using some state and closure essentially. No big deal. Any questions so far? A one-off generator is you have an array of valid inputs, maybe an enumeration, generates one out of it randomly. So here we have days of the week, and this generator make one-off generator generates one out of it randomly, and that's kind just remember the array. Well, in this case, it's initializer list, but probably backed by an array, and that's why I turned it into a vector because the array backed by the initializer list is probably big array. So we remember it as a vector and just look up the days as well.
But why do you have to do that? Oh, okay. No, okay, I'm confused. You're passing the initializer list by value.
Right, and it's not going to. So the array that. So there is going to be an array for that initializer list, right? And that array may go away if it's local.
So why couldn't you just do options equals move list?
That list is not owning the array. The initializer list never owns the array. It's just a range, or does it own? I thought it doesn't.
It's not owning, but you don't need ownership here because
Not in this example. Is in general, if you have an initializer list, I would
well, here all you're
copy
doing
the
is
contents
making-
over.
You're just making a copy of one of the things in the list, right? Or,
Right. Right. Because later on, the idea is to be able to pass this generator around. I don't know. It's my podcast app. Don't embarrass me.
Okay, this is actually returning a lambda that when you call it will give you one.
Is it
Right.
correct that initializer list has like Unix semantics?
Yes.
Really?
It's a view on yeah.
Okay, that's terrible.
It's not a vector
An
that
array view.
owns.
Array span. MD span.
Okay, so we can continue discussion later. That's besides the point. The point is like just keep up and maybe even an enumeration, one out of it. That's that. So we saw closures, right? That was kind of looked like it's sufficient perhaps to generate things because it remembers some state. It's not just a function, so you get a function object. Let me call it function object instead of a closure. And is this going to be sufficient for any kind of generator that we might ever need for, say, property-based testing? I don't think so. Generator is, a function. By function, I mean, actually, I should call it function object. Some state and a function called generate, but it's going to be pretty low level to work with. So I don't think function or a closure is going to be a sufficient abstraction here to build a data generator machinery for property-based testing. The answer in other languages may be different, which are more functional. Functions are the things we work with. Here, objects are perhaps a little bit better. So closures are Overman's objects, and objects are Overman's closures. So kind of if you follow that line of thought, then perhaps we can create a generator template library in template class here in C++. This is pretty much same as the closure part that we saw earlier. Only thing is now we call it generate instead of a function call operator, function operator parent. Instead of that we have generate, and it simply forwards it to the underlying generator function. So we initialize it with any generator function or closure we saw earlier, and simply forwards it down. So this is really structurally exactly same as before. Is this going to be sufficient? Well, it's exactly the same pretty much, just slightly different syntax. The answer is no. So here is how we can use it, but we'll figure out it's probably a very low level. So make generator, or make gen from. So that's a factory method. You can pass in a lambda, and out comes a gen. And looking at the gen's type, gen t, we know what kind of generator it is. We cannot really ask that question to, well, we should be able to ask using the context. I was going to say, we cannot ask that question to a closure, but we can. Because decal type will return type. In fact, that's what it is doing. Yeah. So decal type of function gives us, okay, this function returns me an int, so gen of int, so generator is of type int, and that's the actual implementation. So make range would be just pass the lambda to make gen from, and that's it. So it is slightly a little more, decorated than a bare bones closure. So now you have a type to work with rather than just a completely arbitrary type of closures of the lambda. But the point still holds that this is still low level. It's kind of going to be very hard to work with it. So as it turns out, a better idea, I think, is to be able to compose existing generators. Now we have come from single functions to say stateful functions. That would be a closure function object. From that we came slightly higher level, a gen template. Pretty much the same, not significant difference. But now we'll probably make a much further jump, like over here. Putting together generators and getting a generator out of it. So composing generators turns out to be a really powerful idea. And we can have functions like these, map, reduce, concat. So we'll talk about map in detail. So maybe we can concatenate two generators and get one generator out of it. We can perhaps filter from a generator things that we do not want, those kind of things. We'll go through a lot of them in this talk. So that turns out to be the core idea, that you can create more complicated generators from the smaller ones. Now this design style is, I think, very core to functional API design. So far there were just basically language abstractions, right? We got to an object level, class and object template. But then functional programming takes a different route from object-oriented programming. And now they keep talking about algebraic things. Algebraic things will be, you take this two of the same kind, combine them together, gets one more of the same kind, and keep building that. A tree, essentially, a composite design pattern, if you look. So, I think I had a point there I forgot. So that's what we will do now. Okay, one more thing, yeah. The point was, the composition is not going to be arbitrary. The composition will be governed by certain laws as well. And those laws are where this fancy terminology like monoids and functors come into play, because they are well-studied abstractions, and people say like, look, if you follow these rules, then you can guarantee these all other things. So let's stick, those are guardrails. You stay within them, you can guarantee a lot of things about your code, and it's essentially a pattern that you just see. You see a map function, just immediately expect, what's going to happen, and that's a good thing. All right. Did I mention that all these functions, return a generator? That's why they are. Okay. So here's where we started, right? Just a single generate function, and we'll add map, zip width, concat, and scan take. This can go on and on. There is really no fixed set of operators here. Whatever seems useful and necessary, I simply dump them in the generator class. Yeah, in that sense, it is never kind of done, because instead of adding methods, let's say like friend methods or maybe even namespace level methods, I just dump them into the generator class template itself, because I get this nice dot syntax, fluent interface. All right. So let's look at mapping over a generator. I think this is going to be a really important capability in any generator. So we have a range generator that's, let's see, a range generator that generates random numbers between 0 to 6, and we want to turn it into a day generator. So we saw that earlier. We remembered the options class and options turn it into an array and whatnot. This is an alternative way to do the same thing. So we start with a range in and map over it, and the mapping function is pretty straightforward. Simply returns the corresponding the value from the array. So note that we started off. We had two things to start with: a more primitive generator called range_gen, which only generates integers, and we turn each integer into a string on star actually, yeah, a string via this function. So that's a composition actually. We are not using make range_gen, at least at this level. The map internally does that. We'll see that in a second. But for now, we are looking at a higher level. We go from a generator of integers to generator of strings by simply calling a function. This new degen actually doesn't generate anything unless you call generate. So this is just pretty much a description of your computation at this point. It says I will do it if you call generate. At this point is just no side effect. Is that the right word? No side effects up to this point. Just side effects will be there only when you call generate. If at all you have program side effects. Question?
You have that in a while, so what happens when you go out of range?
Excellent question. I will get to that maybe 5 slides down. That's a great observation. Let's consider this goes on and on forever. It's a random number generator, right? Range_gen is a random number generator. It will just generate values forever. And that's the intention so far in this slide. Okay, so we go from generator of integers to generator of strings. Just talk about that. And we have to 8:30.
Yeah.
So little bit of functional lingo here, functor. So anytime you see map and compute it correctly, it's probably there's a good chance that it's a functor, and it's just you can just say it's a functor pattern. That feels a little more palatable. So, but remember, it is somewhat law. It is lawful. It has some laws you have to follow. One of them is composition law, and this is where it gets kind of very category theory ish, but they're pretty straightforward actually. At least some of the basic ones are very simple to understand. So what this says is, well, your map function is not just arbitrary thing. It should follow some rules. Like if you map twice, so you take a generator, you map over it with function f, and then you map on the. So once you map, you get a generator, right? A temporary one. So over there. If you map on it again, you get third generator. Now that thing is same as indistinguishable outside, maybe different identity, but indistinguishable from doing a map just once, but with the composition of those two functions, f and g together. So here's an example of that. So we started with the range generator, 0 to 6, and we map over it twice. Here is the Fluent API. That's why I like the map to be a member function. We turn it into days. So here is a generator that turns it into gen, a day gen, and we turn them into the days into uppercase characters, uppercase strings. That should be identical to a single map which does both things together. So this lambda here does both. It gives you days, a specific day, and then turns it into an uppercase. As long as that holds, you're good. So that's important. Then there is an identity law which says, well, if you just pass a trivial function like that, which simply returns the input, auto A, return A, then it makes no changes to the generator, at least no observable changes. This must be held true. So even if you do this 10,000 times, nothing observably different should happen. So that's how map should work. So it actually adds some requirements on the functions you can pass as well as on map, the implementation of map. Alright, so those are the two laws, very straightforward laws I think. There are probably more, but I think they are the most important ones. So here's an implementation of map. I think this is interesting. So we are in a generator, right? Start this, and we get a function which is single input, single output, and we call make gen from. That's our factory to create more generators from a lambda. So this lambda remembers this, makes a copy of the existing generator, and remembers the function. And when it is called, it first generates a value of self.generate, and passes it on to the function, and whatever that function returns is the value of the mapped generator. I'll give you a second to perhaps absorb this. I don't know if it's straightforward or not. But the idea is you always, so map itself doesn't do any computation. It only returns a new generator. So nothing really happens, it's just a new thing, no side effects. But when you call generate on that, the whole machinery kicks in, and the internal generate is called, and function does a transformation. If you're familiar with the decorator design pattern, it works exactly the same way. So you have a function, you just call down the chain, and then you can do anything with that value. So although decorator misses on the laws part, that's the main difference. Decorator never says that you have to have this identity and then composition or whatever. But structurally it is very simple. One more thing, that the map function is actually a L value reference qualified, const ampersand over there. It's a const function. It does not change the existing generator. Hence we are making a copy of the existing generator. And it's L value reference qualified. So, well, let's look at the alternative value, alternative implementation, and R value reference qualified function. So, I discussed the difference between these in my last talk in the JFrog meetup. So, this function is useful when we know that there are multiple temporary generators will be created. For instance, when you change this map or any other operation, one after another, a lot of temporary generators will be created. They are all R values, right? So we can always steal the guts from it and use move in those cases. So it's a parallel implementation of map where if I know it's temporary, I just optimize them out. So if it's reference, an L value, then this one will be called. So that means using this style of the fluent interface as well as generating new ones has some opportunities to optimize away because of the R value reference qualified functions. Any questions on this one? All right. So one more abstraction. So we looked at the generator, which is a map, a functor, a map over it. It also turns out to be a monoid. So what does that mean? So it is actually a fairly straightforward concept. Everyone's familiar with integers, and it's just an extension of that with some little more fancy type, which is like a generator. And a lot of types actually can satisfy these requirements, which we will see in a second. So monoid is something that allows you to kind of combine two things together, and you get another thing of the same type. So you add two integers, you get another integer out. You have a map, you take another map, you combine them together, you get the same. You get a map. Similarly, a histogram. A histogram is a map of frequencies. You take another histogram, combine them together, you get another histogram. Similarly, two generators combined together, if the types kind of align, then you get another generator. And how do you combine? Combination is what the key is here. In this case, just an append. So two strings appended together gives you a string, exactly same thing. But we will kind of thoughtfully program that ability into this. So it has this identity law, which says, okay, and anytime when you see M here, just think of a generator or even a string or an integer. In most cases, this should hold even in this part or the monoid case. So there is this notion of identity. So in case of generators, it's going to be an empty generator. Right? I'm coming back to original question about question from back there about calling generate in a loop, whether it ends or not. So it becomes relevant pretty soon now. So there is an identity. So for integers, it will be 0. You add 0 to anything, it's the same value. Doesn't matter which way. 0 plus a or a plus 0. Either way, it's the same thing, same as a. And same for maps or histograms. Histogram with all frequencies 0 will not change anything, right? A generator that's empty, you append it to another generator before or after, it gives you the same generator back. So that's the append operation here, which is the combination and empty generator. So far actually we have not seen any example of an empty generator. It always has this generate method, and it gives you something. There is actually, so far I haven't discussed any empty generator at all. So does that mean it's not a monoid? I think yes, because we don't satisfy the identity law. Unless we have a way to express or represent an empty generator, the generator abstraction cannot be called a monad, because hey, there is no append operation that satisfies the identity law, so no. Well, let's add it, right? So that's what now it's telling you, like, okay, I think if you believe, okay, maybe making this monoid is a good thing because smart people say so, let me make it a monoid, let me see if identity holds or not. Well, it doesn't. That's how we're going to realize, hey, is this really a monoid? No longer, because, I mean, not yet, because I don't have any notion of empty generator. So this generator thing needs to end somehow. Although it's not necessary for my property-based testing, I can always have a for loop 1 to n and just keep working with, generator that never ends. But I thought, hey, let's just, let's do it the right way. So I added a notion of termination to generator. Like now, suddenly all generators now need to terminate somehow, if at all they do. Some generators never terminate. A random number generator, range, they don't terminate. For instance, something like in order generator. Let's say there is an array and you want to just generate each value, n values, and then stop. There is no notion yet, right? So I ended up choosing the simplest possible way to report termination and exception. Not the best way to do it, because termination is very much an expected thing in this design, but I'm okay with that because this library was meant for testing. So I ended up choosing out of range, an exception out of range, as a way to indicate termination of the generator. So yeah, that's in order gen, right? So in order gen essentially generates 1, 2, 3 and needs to end at that, and then you append identity. Either way. So once we have this notion of termination, now it's a monoid with identity law. There is one more law though. Any questions on this so far? Does that reasoning make sense? Why we kind of decided to introduce a completely new notion of termination, which wasn't there, and some other laws will require to perhaps add whole different notions into your design in that sense. So everything actually changes. All implementation needs to handle this try catch. Maybe there are better ways to handle termination. So associative law, this is also rather intuitive. You go from the order in which you, so okay, let's lay out those generators in a specific order. Let's say F, G, H in that order, right? Now it doesn't matter how you group them. So F, G together gives you a thing, then you append H to it. It's the same as doing the other way around. So the grouping doesn't matter, but the ordering kind of does, right? If you do H, then G, then F, think of strings, right? Same as that. Strings are generators of characters, maybe, and they terminate, right? So if you append strings in like this or versus like that, makes a difference. So the associative law is about, okay, once you have, I think the way to understand this is, once you have laid them out in A order, you can have any order, but once you have it in A order, then the associative law should hold. It doesn't matter how you group them. Which means you can run half of them in parallel over here on this machine, other half of them over here in this machine, get the result and combine them. Well, that's basically MapReduce. And for programs for abstractions that actually support this. So it kind of nicely gels with very powerful frameworks out there for big data. Because of the monoid law, it works. You could say that. This would be a C++ representation of the same law over generators. So whether you append in this order or that order, it doesn't matter. Actually, group. I should say group. Order does matter. Change the order, the output is different. All right. So we talked about empty generator as well. Here is, an implementation of empty generator. It always throws out of range. Never succeeds. So now that's an identity. So the return value of this make empty gen is your identity generator. You append this before and after any generator. Get the same thing. Append, it's kind of a screen full of code. I don't think it's kind of particularly interesting, so I think I'll move on because I have few more interesting things to cover. Less than half an hour. So zipping. So now we start to come closer and closer to our objective, which is generating structure types, not the types, the values for say a type. We looked at shape type, maybe a pair. So a pair of two integers, right? I don't care what values those integers have. I just want to say, hey, my type is a pair of two integers. Just throw random pairs at me. Okay, both are integers. I can just create a gen of ints and push values in, right? So each generator of integer will generate integers, but then I have to combine them together because a pair is a pair. So zip is a way to combine multiple generators and generate a structure type. So here, I think this example is just what zip with is meant to do. So here you pass in a 2-argument lambda to zip with. There is xgen, then there is ygen, and it just makes a pair. So zip with calls generate on each generator, in this case x and y, gets two values and calls your function. Whatever your function returns is the resulting generator. So now we are combining two generators at a time. We don't have to stop at 2. We can have 3, 4, 5, n. Our structure is has 17 things, 17 integers. Why not 17 generators? So that's where the composability becomes very important. It is pretty much arbitrarily composable at this point. Well, so far, just a flat pair will create nested structs later on as well.
I have a question.
Sure.
Is there a reason you're putting ygen as the second argument on the zip width instead of like the first argument?
Yeah, I
It
know
seems
that
a little-
question was coming.
Yeah, it seems a little long.
I don't know if it is okay. So, well, maybe this is an answer. I don't know exactly. You could have, let's say, arbitrary number of generators. So a variable number of generators would be a dot 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 in zip width, right? The first thing is always known. You always have to pass a function, followed by whatever many generators. So because it's dot dot dot, it's the last argument.
Yeah, std visit does the same thing because you can visit a variadic number of variants.
Right.
So std visit also takes a lambda and then a bunch of other arguments.
Yeah.
And I think that's totally wrong, and you should always put the lambda last because it looks nicer.
Yeah. Lambda at the end looks nicer, actually. But I don't think we can do that, right?
It takes more metaprogramming. It's like
Ah.
easy to get that right, and it's hard to get the lambda
Right.
at the end.
Right. Okay. All right. So zip width. This is the implementation. Well, yeah, there you go. A generator list, and we just save the generator list here, and just the same thing, right? We call this function. Of course, the function and the number of generators you passed must match. So it is always self with everything else over there. If this function returns a tuple, well, you just got a tuple generator, or whatnot, or your specific type as well. All right. Of course, there has to be monad. So I'll try to give justice to it. It's fairly straightforward for generators. That's what I like about it. And that's why I think something like this should be in an introductory book. So a concat map, that's a function. So we saw concatenation. How about we want to generate output like this, right? So each row, first row has one number, second row has two numbers, third row has three numbers. Clearly we need two generators. One is for the rows. I think there are 9 rows, right? And the row is knows how many digits are there in it. So each row is itself a generator. So there is a generator of generators. We'll look at that in a second. So for the row part, we have make in order gen, and it simply is a list of 1, 2, 3, 4, 5, 4, 3, 2, 1. Essentially, how many elements we want in each row. So in order just goes in order. It just generates 1, then generates 2, then generates 3, exactly, and goes and just stops. Now we take that value, right? So concat map is gonna pick up the value generated by the earlier generator one by one. So this int I here is a value right above the one at a time. So it takes 1 and it generates a stepper generator. I did not quite describe that earlier. But stepper is pretty straightforward. Stepper generator is essentially, okay, let's say 1 to 10, and you want to go in the steps of 1 or steps of 2. So then we go 1, 3, 5, 7, 9, or steps. That's what a stepper generator is. So this is 1 and I. That means start at 1 and go in steps of 1 up to I. That's what it is. Essentially a for loop that you can pass around. It has exactly, you have control how many elements it generates. So we get an I, and for each I we generate a new stepper generator. So the first I, which is 1, gives you a generator of 1 because 1 to 1. And we have actually a side effect here, which is cout/n. So once you start generating values from the triangle generator, for the first value, it generates a generator and prints 1, right? It gets interesting when it's 2. That generator is done, even the stepper generator is done, right? Then for the next iteration, it generates 2, and 2 gets mapped to another generator which generates 2 values. So you can see that the output of concat map is actually something that, not that it's returning a generator. So far we never had a function that returns a generator itself. If this were just a map, you would get a generator of generators. And that's kind of not very useful. So concat map kind of in this case, flattens it out and produces just the final terms that we're interested in, the actual numbers. And we get the number of multiple lines because the slash n is right in the concatenate function. Any question? I think there's a comment back there.
Yeah, so I asked this question a couple slides ago about days. What happens when you had a while true loop?
Yeah.
So I guess in that case you just get a runtime error since you're doing a try catch and you weren't doing it there.
Actually, no, because I briefly talked about how we introduced termination to satisfy monoid requirements. And in this implementation, we indicate termination of a generator by throwing an exception like this. So this does terminate by throwing this exception.
What about the previous one? How do
I think the thing we missed with that, for the previous one was that it was an infinite stream of random numbers, not a set of random numbers. So the 0 and 6 that we passed were the upper and lower bounds of the random range, not the length of the range.
So it always generates random number from 0 to 6.
That's right. Yeah, that one does not terminate. Not all generators need to terminate. Okay, so I think I need to speed up a little bit. So monad laws become slightly more complicated to describe. It's just better to look at code. So or we can talk about it after during dinner as well. So I'm going to skip this in interest of time, but I want to talk about type generators. So there are two notions you may have heard about: return and bind. So those are here actually. A return is creates a monad. You enter into it. That would be a make single gen in this case. It simply makes a generator of single value and terminates. So whatever, make gen of 30, it will generate 30 and then terminate. So that's that. Exactly once. Bind tends to be a little more complicated. So I'm not into it coding here. All right. So that was the mathematics, right? Some of the mathematics of generator API, and what is really going on here? So kind of trying to summarize. So the design principle is that okay, we had these generators, functions, then stateful lambdas, and then a gen template, and now we are suddenly into this different world where our generator is a monoid, is a functor, is a monad, and everything suddenly. And it's like now it's like a really powerful thing because you can combine things together. A lot of things can be achieved with this power. So it essentially becomes a language to solve your problem. The API is the language, the generator itself, the maps and the zip and those kind of things. It gives you the language if you wish. And yeah, we are using implemented C++, so it's like parsing and compilation is free. So this language has primitives like basic generators that don't stop, a little more complex generators like pair and tuples, and you build them from smaller parts, and those are the functions. So this actually forms an algebra, and I think I struggle with that kind of, okay, what is an algebra? It's like, okay, I think that's what it means by algebra, because you start with things and then combine and just get the same kind of thing back. So an algebraic design, or synonymously functional design, synonymously compositional design, should have these things like a first-class abstraction and a lawful abstraction, should follow some laws, and a compositional API. I think whenever you see this, it's fair to call it an algebra. An example of that in standard library would be, well, that's something that's coming up, is a ranges library. At the heart of it, I'm not saying that this is all ranges has got, of course not, it is much more powerful, but this is certainly one of the core designs in it. You always take bunch of ranges, you combine them in this map, filter, where kind of things, and you get another range map. So now with this mindset, okay, why is this particularly designed that way? So here, that's the reason. I'm sure you will find that there are lawful abstractions. It's a monoid, handles those identity combination laws. So that's that essentially, based on mathematical composition, based on mathematical concepts. And we saw them, those concepts, monoid functor. I think I personally haven't found the category theoretic intuition very useful so far. But knowing some of the laws and just making sure, hey, am I satisfying them or not, kind of, okay, I'm probably in the right path. So having those guardrails kind of helps, like in subtermination. But my understanding was they were from, okay, here is a thing called monoid. Let me create a monoid. And it's like, well, no, I think I went the other way around. It's like, create what you need and then see if it kind of fits in this larger design. Okay, so we are back to our property test. We have all it needs to generate data. So let's move on and any questions on this so far? In the last 15 or so minutes, we're going to talk about type generators. Okay, so I'm going to submit that if we can generate random numbers at compile time, then we can generate random types as well. How is that possible? How do you even generate random numbers, right? One way to do it, well, any ideas on it so far maybe? Before I dive into
Not an idea, but can you enlighten us? Why would you want to do that?
Right, so remember the earlier property-based test, right? Here is a test. The test needs a type and data. So in is data, well, we saw a systematic way to generate data from random numbers. But it also needs a type. So now you can manually create a few types, sure, and test it. But why only those examples? Why not arbitrary types? And how do you make sure that your types, whatever you have come up with, cover all possible cases? And even with automatic generation, it is not possible to cover all possible cases, but you may get significantly more confidence in your code that you can throw any type at it, it will handle it. That was one of the goals I had in mind for property-based testing. So, question?
Well, yeah, like an example is like, let's say that you're like implementing std sort, and you want to make sure that std sort works for any type that has, for any type in the comparison operations, as long as certain property holds for the comparison operation. Well, there's a lot of types out there, so it's hard to like come up with a list of all the things that people might want to do. And so anytime you're writing a generic library interface that should work across a large set of types, you might want to generate types.
Okay, one very simple way to do that is you ask the shell to generate a random number. You do that with $random to just give you a number. So here, I'm assigning that random number to foo, and I just print it out. Here's one run, it just printed 17695. A totally random number. But that's not enough, right? You need to generate types for this. Well, now there is this magic thing called LFSR, and it's a function. So we got random the same way as before. Actually, it's a seed. And that's the first value. This is actually just for as an example, not really the actual type generator. So simplest example. So test foo is a number there, and bar is the result of LFSR. So what is LFSR? It is this. It's a const explorer function, and I'll give you a few seconds to look at that. As you can see, it's kind of fairly hairy, bit manipulation, bunch of XORs. It's like God knows what it's doing. So it's actually not any magic incantation at all. Comment?
I might be ruining the next slide, but
Okay.
you can seed with, you don't need to seed with like some command line parameter. You can just use like underbar time.
Oh, okay. All right. So compiler generated random
There are some,
yeah.
there's some pre-compiler, pre-processor macros that you can use to see, people have done this to write.
One of- One of the reasons to use shell was to dump that value as well.
Yeah.
Maybe you can do that with compile generated. Why not? Just first line. So LFSR is that function. It's const export function. So all the computation is done at compile time. So whatever value foo has, whatever value came in as a seed, gets massaged with this crazy bit manipulation. It's called linear feedback shift register. Well, that's just no output. It's kind of pretty. I'll go to the next slide. A linear feedback shift register. Really interesting thing. I do not understand how how this mathematics even works. But pretty crazy and very useful. So it is essentially, you can represent, this is a 4-bit LFSR register. When you have a circuit like that, you initialize it with anything but all zeros, just any value. So let's just pick here. And you add an XOR between those taps, those last two things are taps, 3 and 4 I think in this case, and you feed the answer back into the head. It's guaranteed to generate all possible permutations of 4 bits except 0. Guaranteed. So these are 16 values guaranteed generated. And that's called linear feedback shift register. There is a whole science, mathematics behind it, how this can be a good quality generator would be that covers entire spectrum without missing out on any of the values. So we want that, right? So with 16 bits, it looks something like this. Now you're talking about a 65K values generated using this mathematical idea. And that's the feedback polynomial. You can go on Wikipedia and read all about it. It's very interesting, and there are a lot of funny things you can do with this. But for me, I look at this, wow, it's all integers, it's C++, const export, and done. It just generates, you just feed in a random seed. The LFSR that I implemented, you saw earlier, was the 16-bit, the implementation of this, two const export functions. You just plug in some value and it's guaranteed to go through the entire 64K values and come back. Well, so that means we have a way to generate random numbers. They look seemingly random, actually, right? I mean, they are actually not random. They are very much predictable. But that's exactly what we want. We want reproducibility, although seemingly random. Once you have 32-bit LFSR, it's going to be just vacuous. Like, probably won't be able to generate all the values. I ended up generating all values and tested that. I'll come to that a little later. So this is that, and very simple to implement, right? With the const export function or just a hash define. So now you've got those values, compile time constants, integers. You just map them into types. So in this case, so this is the type generator part. I map 0 to int, 1 to char, 2 to float. So you have some 13 or so primitive types. So 0 to 13 map to that. And any higher value, now you can think of, okay, how about a vector of characters or vector of anything? So the 14th value would be a vector of, you apply type map over and over again, recursively. So first 13 will be a flat terminating conditions, 13 values, 13 character type, 13 primitive types. And the 14th one, let's say for example, could be, okay, I want to build slightly more complicated one, a vector of something. So I get vector, or what is that something? Well, you call LFSR on that value again. Maybe I should go to the next slide. Yeah, so here is an example where we generate a tuple of 3 random types. Whatever seed that comes in, we call LFSR on that, and mod 4. So in earlier example, we had just four things in the type map, right? Third one is 0, 1, 2, 3. Third is double. That's a double. Let's see how it works here. So mod 4. So whatever seed comes in, value 0 to 3, we got some type there, because type map. The output of LFSR, we feed it to LFSR again to get the next seed, and on. So the third one is 3 applications of LFSR. So this is of course not truly recursive, it's just 3 things, but I think you get the point. So now you have a tuple, depending upon whatever random number is generated, you get different tuples every time. So you can see that here. For instance, in this particular case, it's a float double and character. All right. So seed changes, the types change. Now all you need for a more generalized version of this is a little more metaprogramming. I'm not really going to show that because it's fairly straightforward actually. Like for instance, if you want to create a tuple, then well, okay, there is a case for tuple. Let's say our 15th value is a tuple of, let's say, tuple of how many, right? How many members? Well, another random number. So you call an LFSR on that again. So you just keep calling this LFSR over and over again, and keep mapping them into types. Does that make sense? This can be implemented recursively with some metaprogramming, very basic metaprogramming actually. And if you want to see the implementation, it's over there, type generator. But it's a little more complicated than it needs to be because it covers many cases and avoids creation of same type over and over, avoids those kind of things. So it's a little more complicated than it needs to be, at least to understand the concept. All right. So that's basically it actually. Type generator is essentially generate random seed and map them to types. So now you have, say, tuple generator, a pair generator, that's just 2. What am I missing? In that property test actually, I also had to generate member names. So a tuple has no member names really, it's just positional, right? But the underlying library, DTSX types, needed, hey, okay, this is an integer, but what do I call this guy? Well, a string data generator, right? For that, it would just whip up new numbers, new strings, ordered by M1, M2, M3, M4. So that was there too. That's it. So with that machinery, you can create a serialization and deserialization library which you can test, and you just pass in a lot of types and generate random data. So what did I end up doing? So I discovered some good numbers. For instance, this is with 16-bit LFSR. That seed, 31415, created a nice little 3 nested structs with tuple inside tuple inside tuple. And it was really easy, my most favorite number, because it was very easy to test. Once you get the thing right up to 3 levels, it kind of works with n pretty much. Then some other numbers ended up creating 51 nested structures. It's impossible to even look at that tuple. And I don't even need to, because if the program compiles, then I just go to next test case. So the continuous integration test would actually generate different random numbers and would just run the same test, or compile the test and would run it over and over again. So some pretty interesting numbers. Then I discovered some really bad numbers. And bad in a sense, they were my nightmare. In a sense, I just could not make the library to work with that. So it ended up creating a tuple of 2 megabyte static size. Right? You can imagine, right? It has got, it's segfaulted. So it had vectors of tuples. Imagine a vector of 51 nested structs, something like that, and it would just allocate, okay, 300 of these, and 500 of those. Even the sizes were randomly generated. I had to kind of bring it within control, but you can do that with those, map and filter and kind of functions. But if you want to let it loose, then it crashes, and then it's like, okay, maybe I don't have to debug that. Because who creates, such a tuple? But it created it, So I ended up actually 64K numbers is not hard to generate. So over 2.5 weeks, it was running on my machine overnight, day in, day out. and it generated all the cases, 64K, and I saw whether it works or not. There were maybe about a dozen or so really bad numbers. It just crashed. I didn't bother to look into them. But for all other values, all the types it generated, it would print them out. So I would just share with my colleagues, hey, look, I got a 51 nested structs. Like, you want to look at this type? Here you go. And it would just scroll pages and pages. And yeah, with 32 bits, yeah, it's not probably never going to. Like, with 64K, it took about 2.5 weeks to finish the entire range of those numbers. Right, that's basically it. Thanks a lot for listening. Any questions? I'll be up.
The important question is, how many bugs did you find?
Actually, I did find some. First of all, the implementation of the generic part of working with Fusion and all those things had many bugs. And bugs in a sense, it wouldn't just compile. It would run into cases where I don't know. I don't exactly recall. So that's just embarrassing. That we claim that it works with arbitrary types. It better compile with it, right? Then is the next thing, which is runtime. So most of it was useful for making sure that it works with arbitrary types. And then we did discover some corner cases because the underlying library was fairly well tested as well. But we did discover a corner case where, in case of two inherited types, when the last type was like of higher alignment than the first member of the derived class, then it would just scrap out. And we discovered that purely through accident. It's like, what is wrong with this type? Looks perfectly fine. It's set false at runtime. It doesn't look like it's library's fault. It's probably something underlying. So it created that unique case out of nowhere, and that is exactly the purpose of property-based testing.
In the talk, you referred to various header files. Are those all? Can they be found in the GitHub repo that was linked and
Yes.
meetup? Okay, I just want to make sure I knew where they were.
Yeah.
So if I understand correctly, you were basically applying this to test an existing library, right?
Well, not existing. The library was created and testing. This library was created for testing that library.
Right, but I guess what I was getting at a little earlier when we were talking about seeds, if it seems like if you have a library where you have people actively developing on it and changes being made, you don't want your CI, you want like your CI testing to be 100% reproducible, because otherwise when something breaks you don't know whether, oh, this broke because it's always been broken and just hit these test cases that we never saw before, or oh, it broke because this person changed something that broke something. So it's sort of like when you say CI, I think maybe you're meaning that in a different context.
So let's see. If you know that with some certain number of iterations, you reach to a point that you feel confident. Okay, I think this is stable enough. It has covered enough number of cases that I can actually have CI do this. And if it breaks, maybe it's the new code's fault as opposed to finding out a random number that this never worked for. Initially, you definitely don't want it to be in the CI because it literally breaks all the time. But then, as it matures, it gets harder and harder to break it because it's actually right. But then, it never was, like I said. In some cases, it always set faulted. So I wouldn't put this in a CI because it actually takes whole. I don't know. You could. Well, the CI minimally at least has to dump the seed keys and then take it from there.
Sure.
Yeah. Okay.
Probably missed something. But if you're going to let it, in the case of the 16-bit LFSR, when you let it go through the entire set of numbers from 0 to not 0,
Not
from
0.
1 to
Right.
2 to the 16 minus 1.
Yes.
Why not just do them in order?
You could.
I mean,
You
is there
can-
any
you can
merit
do
in
it.
using and changing the order? Is there merit in having them appear in a sort of random order?
I think it makes sense when you have like 32 bits.
When you're not going to be able to do them all?
Right.
Okay.
And
You
then
just hit
you
more
hope
parts of the
that
space.
it's kind of fairly randomly distributed and it will catch it if there's a problem.
Well, there's actually two different orders of traversing things here, right? There's, on the one hand, we have 64K seeds. Let's just search all the different seeds for the LFSR, and that you can just do with
That's,
Yeah.
that's what I'm,
But the LFSR itself, you know, is being used to generate these tuples of things where you don't necessarily want type number 1 followed by type number 2 followed by type number 3. You want some degree of randomness, quote unquote, in that process. So that's why the LFSR is involved at all. But yeah, for searching the different seeds, just go through them in order. Shouldn't matter.
okay.
Have you had any experience with generating classes with different sort of mixing capabilities, like come up with a set of properties, like I don't know, like move constructibility versus non-move constructible, and then like different, like whether or not they have different comparison operators, and then like I want to generate a set of types that have combinations of these properties. Do you have any experience with?
Not directly like that. That sounds like perhaps an exhaustive list of type examples would may cover it, like non-movable, maybe.
Yeah, I'm thinking yes, but I don't want but if one did not want to enumerate them, they would probably want to use a generative approach like what you have.
Yeah, it seems like it should be possible. Okay, so let's say you have a template that takes arbitrary number of types, and those types actually are mixins,
Yeah.
and now you inherit from them. Perhaps that's a way to do that, and then
That's what I was thinking.
then I guess now it's a matter of generating those template arguments in some order. Thanks so much.
Okay, thank you.